All right, look at the next slide. Look at the next slide. Where's the next slide? Eh, yang ni pula. Nah, this one. Yeah. Okay. And here we need to distinguish between phase velocity and group velocity. This is a common point of confusion. So let us keep it simple. Phase velocity tells us how an individual wave crest move. The wave, look at the crest. Okay, that is phase velocity. How fast the wave crest move is phase velocity. Group velocity, however, tells us how the overall wave packet, the complete wave packet, how the overall wave packet move. Just like the photon, the light, a photon is made out of a wave packet, and how fast that wave packet moves is the group velocity. So in many real physical situations, group velocity is more important because it is linked to how energy or information travels. Energy and information. The optical fiber, because we carry information using light because it travels faster than sound or even electron. So in a crystal, these two velocities are not always the same. The phase and group velocities, they are not the same, not always the same. That happens because the dispersion curve is not always a straight line. Remember the dispersion curve? The optical dispersion curve? Or the acoustic dispersion curve? It's not always straight line. So this slide teaches us an important lesson. The shape of the dispersion curve affects how vibrations actually propagate in the crystals, whether it follows the optical or acoustic. Now, yang ni okay, jelas lah. But you don't need to memorize all the equations, as I mentioned before. Any equation will be given in the if it includes some calculations, it will given in the appendices. Nah, but this one is not a calculation. This one more like a derivation. So definitely, I will not ask question about the derivations. Now this one, we focus on the long wavelength limit. Long wavelength limit maksudnya K greater than 0. Okay, from the gamma point, it moves left or right, and the K is greater than 0. Right. So this means the wavelength is much larger than the spacing between the atoms. In that situation, the crystal starts to behave more like a continuous solid instead of a collection of separate atoms. So this is very useful because it connects microscopic physics with familiar material properties. For example, this is why we can connect vibration behavior with elasticity, stiffness, and sound speed. So this limit acts like a bridge between the atomic picture and the engineering picture. And this is why it is so important. It tells us that if we zoom out enough, a discrete atomic chain can behave like an elastic medium. Look at that, the continuum connection. We have the Vs. Vs equals to square root of Young modulus over density. If we know the acoustic curve, if you still remember the acoustic curve, at short k, at small k, we have Debye model. And from Debye model, from the slope of Debye model, we could calculate the Vs. And from the Vs, we could calculate either the Young modulus or the density. Kita boleh kira. But the limit is if the K is at the smaller K. But if K is greater, much greater, bigger K, the one is very different depending on the every vibrations of the atoms. Now we look at 5.2. This slide shows the dispersion result for the diatomic chain. Diatomic, not monoatomic. Again, we don't need to read the full formula aloud, because the formula is just to show you what are the relations that we have. Right. This is diatomic. Maksudnya in one linear chain, we have two types of atom. One is small, one is big. Okay, so we have two types of atom. There is diatomic chain. The important result is that there are now two branches of vibration. Two branches of vibration. This is different from the monoatomic case, where we had only one main branch. So the extra branch appears because the repeating unit now contains two atoms. And there are more possible ways for the system to vibrate. So at long wavelength, one of these branches behaves like ordinary sound-like motion. The other behaves differently and stays at higher frequency. So the big lesson here is that the internal structure of the crystal creates new vibrational possibilities. Kan, dia kan ada different phases, kan. Ada yang sedang vibrate ke sana, ada yang sedang vibrate ke sana. Jadi macam tu. Kan? Dia tak akan sama. So this is the most possible way of how the optical phonon could be created from the diatomic chain. If our crystal is not germanium instead of gallium arsenide, so we have two different sizes of atoms, kan? Most probably, we could have both acoustic phonon and optical phonon. Why? Because if we have diatomic atom in one linear chain, maybe at certain K or at certain wavelength, both of the different size of atom, they could vibrate at same frequency. And maybe at certain wavelength or certain K, they vibrate at different frequencies. So during the time when they vibrate at same frequency or same propagation, they are creating acoustic phonon. And at certain wavelength, at certain K, they start to deviate. The frequency start to deviate. The propagation is now the opposite way. So we have this kind of vibration. So we will have the second type of phonon, that is the optical phonon. So if our semiconducting material contains more than one atom, for example, cadmium selenide, cadmium sulfide, cadmium telluride, so on and so forth, most probably we could have two types of phonons. One acoustic phonon, the other one is optical phonon. But if our material only consists of germanium, most likely we will only have the acoustic phonon. Maybe not all, but mainly we could have that one. I hope you still remember what we have discussed this morning, kan? Harap-harap je lah. Right. So we have apa ni, saya pun tunjuk lah, what is M1, what is M2, what else. The periodicity, the A, okay, the lattice constant, the distance between the A, the M2 and another M2, or from M1 to another M1. Apa lagi? We have force constant, it's an identical spring connect, nearest neighbors. This is simplified model lah, spring constant or force constant, kan. Kalau spring betul, kita ada mu, kan. Kita ada mu K. Sorry, not mu K. Yeah, we have mu. This the constant of the stiffness coefficient kalau spring dalam kereta, betul kan. So the displacement also mentioned over there. Stay in the call. Okay. Sikit lagi saya nak tertendang diri sendiri. I have to stay in the call. Alright, now what else do we have? Look at slide number 13. Slide number 13. Nampak macam banyak persamaan kan, Bad? Lupakan persamaan. Tengok dia punya connection. Now we can clearly name the two branches. The first branch is acoustic branch. acoustic phonon, acoustic branch. So in this branch, neighboring atom tends to move together. The first, second atom, third atom, they tends to move together, especially for long wavelengths. This is why it behaves like a sound, like sound, and why its frequency becomes very small near the center. Sound near the center, the gamma at gamma k equals to 0, and the frequency also 0. So it behaves like a acoustic, kan? K0, wavelength 0, dia punya frequency also 0, just like acoustic. Because gamma point is the center of the FBZ, the first Brillouin zone. We always refer to that one when we want to start to analyze. So the second one is the optical phonon or optical branch. So in this branch, the atoms in the basis moves against each other. Optical branch kan, moves against each other. Dia ke sana, dia ke sana. Dia ke sini, dia ke sini. Kan? And because of that, the vibration can remain active even the wavelength is very long. So the easiest way to remember the difference, acoustic means the atom moves together, ni acoustic, and optical means atoms move oppositely. That's all. Begitu cara nak ingat dia. Now, look at this slide. Slide berapa ni? Oh lah, saya tak tunjuk ke slide tadi ni? Betul lah. Oh, saya miss. Ya. 12 ni dah. Sekarang ni 13. Oh, saya lupa nak tunjuk 13. Sorry guys. Leka sangat. Alright. 13. Then now it's 14 lah. This one. Oops. Sana. Alright. So we have mainly discussed ideal models. This slide shows how these ideas look in a real material, for example, silicon. Real crystals are more complex than ideal textbook chains, but the main features still appear. You can still identify acoustic behavior and optical behavior. Kat sini kan. Easily, you could identify optical and acoustic behavior. The one, look at the, saya tandakan dekat sini. Ni kat sini the center kan, the center over here. Pak, kita ada gamma. Gamma bentuk yang macam ni. Tu gamma, ni gamma, nampak ni, gamma. Pak, 000, 000, that is gamma. The first Brillouin zone, the center of first Brillouin zone, that is gamma. So the one that behaves like this, nampak ni, sini, nampak ni. Ini acoustic lah. This is acoustic phonon. This one as well, this is acoustic phonon. Right? Yes, acoustic phonon. And this one, this is optical phonon, where at k equals to 0 or gamma, the frequency is not 0. Nampak? The acoustic phonon at k equals to 0, the frequency must be equals to 0. So itu dia kat sini, dia menjunam kat bawah sini, kat sini dia menjunam. Yang ni, yang bentuk macam ni pada titik sini dia tidak 0, ini adalah optical phonon. So the red is optical phonon, the dotted line yang ni pun nampak ni, dotted line ni pun optical phonon kan. So this is also a very simplified version of the phonon dispersion graph. Sebenarnya graph dia yang sebenar dalam eksperimen sangat packed, sangat padat. By the way, this is the old jacket from FIS tahun 2008, 2009 kita buat ni. So dalam dia ada kain apa ni nama dia? Untuk blazer tu kan. Sejuk dalam dia. Ni. Tada. Dah tak ada jual lagi dah. Ini pun logo UMP lama. Ini logo UMP lama. Itu. Design dia sangat old school. Tapi okey lah jaket ni. Tak adalah flap kat sini, which I don't know what is the function of the flap kan. Pocket pun banyak sangat pocket. I have pocket inside. I think I have pocket over here. Oh tak ada. Ada pocket kat depan ni. The zip also very sturdy zip. Zip macam YKK jeans apa, jeans Levi's kan. Very sturdy one. Anyway, we continue lah. Apa tadi? Okay, now you can also compare the real curves with simplified models. Now, the Debye models gives us a useful approximation for the acoustic branch, especially near the center at nearby the k equals to 0, kan? And at small k. So we have this Debye model. We know that Debye model is not realistic enough, kan? But from the Debye model, we could calculate the slope of the acoustic phonon, and from that slope we could calculate the Young modulus or the density of the material, kan. So the Einstein model pula yang dekat optical branch tadi tu, it gives a useful information where the frequency is relatively flat. So this slide help us to connect simple theory with real material behavior. Einstein cakap all the atoms vibrate at similar frequency, but it's not true, because from the experiment we got the optical phonon. It's not a straight line, it's like a Gaussian curve, so like a bell curve. Yes, it might reaches the maximum frequency, maximum frequency exactly at the same spot with the Einstein model, but later it will go down back again at higher k. So the simple models are not perfect, but they are very useful for understanding the main trends. Later, I will show you a paper written by Amirul Edham, one of our postgraduate, and our first Cytex president. He's a PhD student at UMP, and also I'm the co-writer of that paper. And we try to modify the Debye model that could suit the quantum dots. Nanti saya share paper tu. There are lots of opportunity for the student to do postgraduate study. Let's see slide 15. The quantization of elastic waves. Okay. So far, we have described crystal vibration using the classical wave picture. Now we move to the quantum picture. So in quantum physics, vibrational energy does not change in a completely continuous way. Instead, it comes in small discrete packet. Sebab quantization is not continuous. It's small discrete packet, one by one coming in. And that idea is called quantization. Comes from the word quantification, quantity. We could quantify the things that are coming in. What are coming in? The vibration. Quantization. The vibration comes one by packet, not continuous flow like water, because we cannot calculate how many water has come in at certain time, kan? But if it comes with packet, for example, one packet, 1 gallon of water, second gallon of water, now we could quantify that. So quantization, that is the idea. So this is important because the classical picture alone cannot explain all thermal behavior correctly. We need quantization, especially at low temperature. So unpredictable. So this slide marks an important transition. We are moving from classical vibration to quantum vibration. So that quantum viewpoint leads us to the idea of phonon. Okay. So the quantum unit of lattice vibration is called a phonon. The vibration the vibration of atom inside the lattice. So the quantum, the quantity unit of lattice vibration is called phonon. The packet is called phonon. Packet of lattice vibration is called phonon. A phonon is not a particle like electron, but it behaves in a particle way in many calculations. Sometimes it has that duality as well. So we call it a quasi-particle. It's not really particle, but sort of like a particle. So it is quasi-particle, partially particle, half particle, or quarter particle. How many percentage of the real particle? That is phonon. So this is a very useful concept in solid state physics. Instead of always thinking about the entire crystal vibrating, we can describe the energy in terms of phonon, the small packet inside that crystal. We have this atom and that atom, and that atom vibrates in certain lattice, and that lattice vibration is called phonons. Cumulatively, we have total of vibration inside one crystal. So that phonons also, just like light, it carry vibrational energy through the solid. If light, the photon light is called, packet of light is called photon. It carries the energy of light, but a packet of phonon, it carries the vibrational energy, which propagate through the solid. So these phonons also play a major role in thermal properties. So if you remember just one sentence from this slide, so it should be like this. A phonon is a quantum packet of crystal vibration. That's all. Phonon adalah paket terkuantar getaran kristal. Boring bahasa Melayu. Macam bahasa sastra pula. So a phonon is the quantum packet of crystal vibration. So itu dia maksud phonon. So we take a break for a while. Later we discuss back again, starting from slide 17. Right.